In this video, we present our work entitled Deep Reinforcement Learning for Instruction Following Visual Navigation in 3D Maze-like Environments. With the technological advancement in the robotics and artificial intelligence fields, the tasks we expect the machines to perform are becoming more and more complex. Unfortunately, explaining how to perform such complex tasks using classical programming languages is often more challenging than the tasks themselves. For this reason, the ability to understand and follow natural language instructions is one of the most attractive skills for tomorrow robots. In this work, we address the problem of instructions following visual navigation. Visual navigation is a very challenging task. The agent must be able to localize itself, recognize obstacles, and plan a route with the use of visual inputs only. Instruction following visual navigation is even harder, since the robot must also comprehend a natural language instruction in order to follow a predefined path. Despite different approaches have been proposed in the last years, they are all based on the assumption that the environment contains objects or other elements that can be used to formulate instructions, such as houses or offices. On the contrary, we focus on situations where the environment objects cannot be used to specify a navigation path. We show that without reference points, visual navigation and instruction following can be rather challenging, and that standard approaches cannot be applied successfully. To address the problem, we introduced a novel recurrent convolutional neural network trained by using reinforcement learning. The proposed architecture is fed with the current frame from the first-person view of the agent, and with the instruction describing the path to follow. The first network component, in yellow, computes the direction to take in the next intersection along the path, given the current image and instructions. The visual frame is processed by two convolutional layers and is concatenated with the instruction embedding produced by the GloVe model and a bidirectional GRU. The extracted features are fed into a fully connected layer, followed by a bidirectional GRU and the last fully connected layer, which produces a vector representing the probabilities associated to each one of the possible directions: right, left, and straight. The input frame and the class D of the estimated direction are then combined using the Hadamard power. This means that the next direction directly affects what the agent sees. The processed image becomes the input of the second part of the network, in blue, which outputs the policy pi and the value function v. The policy pi is a three-line vector that represents the probability to choose each one of the three possible actions: turn right, turn left, and go forward. Our model is trained end-to-end with deep reinforcement learning using Impala. We built 12 independent environments, and in each of them we placed an instance of our agent. At the beginning of each episode, the agent is randomly spawned and tries to complete the path by following the instructions. Each time the agent reaches the next path cell, it receives a positive reward of 0.1, otherwise 0. To prevent the agent from getting lost in the environment, and therefore no longer receive any non-zero reward, we assign to the agent a -1 reward and reset the maze each time it exits the path. An episode ends when the maximum number of 900 steps is reached. We choose 3D maze-like environments as our test bench, since they can be very large and offer very intricate structures. In particular, we consider two different scenarios. The wall environment is a maze-like environment characterized by straight floor and walls, and by a minimal visual complexity. It is completely free of objects or reference points that can be used for localization. The garden environment, on the other hand, is a photorealistic maze-like environment characterized by a rich vegetation that considerably increases the visual complexity. The various elements within it, including grass, flowers, rocks, and trees, make the detection of the intersections significantly harder. However, none of the elements can be used by the agent as a reference point during the task execution. For training, we consider only 6x6 mazes. However, to demonstrate our model generalization capabilities, we tested in hundreds of mazes with 4 different sizes: 4x4, 6x6, 8x8, and 10x10. As can be observed, 10x10 mazes are much larger than the ones used for training, and are characterized by significantly longer paths and instructions, dramatically increasing the task complexity. To evaluate how fast our agent can complete the paths, and primarily how closely it follows instructions, we propose 2 kinds of experiments. In the unconstrained navigation experiment, the agent is placed in a randomly generated maze, and its goal is to complete the path as fast as possible. The agent succeeds if it reaches the end of the path before the maximum number of 900 steps is reached. In this experiment, the agent is allowed to leave the path and freely explore the maze. In the constrained navigation experiment, the agent is placed in a randomly generated maze, and as before, its goal is to complete the path as fast as possible. The agent succeeds if it reaches the end of the path with less than 900 steps, but without leaving the path or turning back. We compare our approach against 3 baselines. The first one is the concatenation model, a simple baseline that differs from our approach in that the features extracted from the current frame and the embedding of the whole instruction are simply concatenated. The second baseline is the gated attention unit, proposed by Chapleau et al. The last one is the sequence-to-sequence model, introduced by Anderson et al., that we adapted for our specific reinforcement learning settings. The tables show the model's performances in terms of average number of steps and success rate in the whole environment as a function of the maze size. From the tables, it can be noticed that our method is the one that achieves the best results in most cases. The plots show the model success rate in the wall and guarded environments in function of the maze complexity. As can be observed, our approach consistently outperforms all the other baselines in both environments and in both constrained and unconstrained navigation experiments, regardless of the complexity level. It should be emphasized that even if trained in 6x6 mazes only, whose complexity range is highlighted in gray, the model can still achieve reasonable success rates also outside that range. Now, we can evaluate the performance of our approach through some practical examples. On the left, it can be seen the video frames that are fed in our model together with the instruction provided below. On the right, a top-down view of the maze is shown, in which the agent, the red dot, and the path it should follow, outlined in blue, can be observed more clearly. With our experiments, we showed that classic approaches are not suited to address the problem. Although they proved good navigation capabilities, they often failed to correctly ground the instruction to the intersections along the path. To take a step forward in this direction, we presented a new architecture that explicitly learns both navigation policies and direction estimation.